everyone. This is Alex, and welcome to the mathleague.org YouTube media channel. We'll be talking about sprint problem number 14 from test release 12116, the March 2021 middle school test. So let's take a look at what this problem is saying. How many positive integers n are less than 300 and satisfy the property that the greatest common divisor of n and 300 is equal to 2? Well, if GCD of n and 300 equals 2, then that must mean n is even because it has 2 as a factor. But it also means that 2 is the only common factor of n and 300, right? So only common factor. So we can actually go ahead and write n equals 2k for some integer k, right, for the time being. So then k must be relatively prime to 300. In other words, GCD of k and 300 has to be equal to 1. Remember that relatively prime means that the GCD of those numbers is 1. Right. So what are the distinct prime factors of 300? Well, if we prime factorize, we'll get, well, it's a multiple of 5, so you get 60. It's a multiple of 5 again, so it's 5 squared times 12. 12 is 3 times 2 squared, right? So you have 300 equals 5 squared times 3 times 2 squared. So the distinct prime factors are 2, 3, and 5. All right. 2, 3, and 5. So now we need to find the number of integers k from 1 to 150. Number of integers k between 1 and 150 that aren't divisible by 2, 3, and 5. And why is that? Because, well, the GCD has to be 1, right? And if you're relatively prime with 300, that means you don't share any of the factors 2, 3, and 5. Okay, so our central goal now is going to be showing that we can make this quicker by using what's called Euler's totient function. In other words, if you've ever seen this notation before, this guy, or sometimes this, there are different notations to mean the same thing, which is to say phi of n is the number of positive integers less than or equal to n that are relatively prime to n. Now, okay, I'm going to go ahead and make room for this definition. What is the Euler totient function of a positive integer n? Well, as I mentioned, it's the number of positive integers less than or equal to n that are relatively prime to it, right? So what this function does is, for example, right, if you have phi of 30, well, we can just brute force that. We can list everything out and find out it's going to be 8, right? But how do we make that quicker, right? Like for larger n, it's not really feasible to list everything out. But you can generalize the idea by prime factorizing and thinking to yourself, right, what integers would be relatively prime to that? So they can't share any of the prime factors. Like 30, for example, the prime factors are still 2, 3, and 5, right? So what if n were an even number, right? Let's just consider that case for now. And I'm simplifying a bit here, but for the sake of example, let's kind of pretend that n is a power of 2, right? So the other prime numbers as part of a prime factorization can just be kind of generalized in the same way, right? So for example, like n equals 16, for instance, well, we know that's 2 to the 4, right? So what positive integers under 16 are relatively prime to 16? Those would just be the odd numbers. In other words, half of the integers under 16. Therefore, phi of 16 is 8. So now instead, let's try something like phi of 27, which is phi of 3 to the 3. Now, what integers are relatively prime to a power of 3? Well, the non-multiples of 3, right? So that's 2/3 of all of the numbers under 27, 18. So you see what pattern we're building up to right now. Basically, for every prime factor in that prime factorization, you want to exclude all the multiples of p. So we essentially want the product of all the terms of the form 1 minus 1 over p, where p is the distinct prime factor. Should I say p sub I, where the distinct prime factors are like p sub 1, p sub 2, p sub 3, up to some p sub j. It doesn't particularly matter what the j is, but we'll just take this product over all the prime factors, is what this is basically saying, right? So the PIs in this prime factorization guy in rigorous notation. So you can prove that kind of less hand-wavily with like the principle of inclusion exclusion, but I'm not going to be getting into that too much for the time being. But if you're interested, then yes, definitely look into how you can apply principle of inclusion exclusion there. I would say start off with things like 12 and 18 that have like 2 prime factors and slowly build up to 3 and 4 and try to generalize that to any number. But anyway, using our phi function, right? In this case, phi of 150, which gives the number of positive integers relatively prime to 150 that are less than it. Well, 150, that's 5 times 5 times 3 times 2, 5 squared times 3 times 2. So again, 2, 3, and 5. Now, according to this, product of 1 minus 1 over p sub I. Well, p sub 1 is 2, p sub 2 is 3, p sub 3 is 5. So we're going to go ahead and write 150 times 1 minus a half times 1 minus a third times 1 minus a fifth. And we can calculate that to be, what is 75, 50, 40, right? So that's our answer. And hooray. What do you know? We're done.
Hi, everybody. This is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.